Welcome back, and in this video we will introduce the shear stress formula tau is equal to VQ on IT. And then we will look at some real life examples of when this shear stress formula is applicable. I guess in this series we'll kind of work backwards, so hopefully I'll try to excite you first with some real life examples and then get into the messy part of the derivation process of the formula, which we will do in part 2 of the series. So the first thing we notice here in this formula is that there is a relationship between the longitudinal shear stress, the vertical shear force V, the first moment of area Q, the second moment of area I, which is the moment of inertia, and T, where T is the width of the section at the location of where shear stress is determined. Now let's take a quick example of how this formula works. Say we have a rectangular beam with a width B and a depth D and a maximum shear force V. Then the second moment of area is simply BD cubed on 12. Now the first moment of area is the sum of area bar, this dashed area here, multiplied by the distance y bar. Now what is y bar? Y bar is simply the distance from the geometrical centroid of the entire section to the centroid of the shear area we are interested in. In this case, we know that the maximum shear stress occurs at the center of the section. So we must consider the entire area above the line that we are interested in, so above that line where it passes through the geometrical centroid. And T, in this case, is equal to the width B. And because B is constant throughout the beam section, so T is equal to B. If we work all this out and substitute in the shear stress formula, tau is equal to VQ over IT, we will get the maximum shear stress in a rectangular beam to be 1.5, which is 3 over 2, V divided by B times D. Now this is just a super quick version of how this formula works, but hey, I think we will discuss it more in detail in part 2. Okay, now let's get to the exciting part. Evaluating shear stress is extremely important when we mainly have built-up sections. Here are some real-life examples which I have also worked with that we need to consider the shear stress formula. The first example is very common in a residential building settings, where we have an upper wall overhanging a lower floor beam, B1 in this case. And B1 here is supporting floor joists, upper wall, and most likely the roof loads as well. So to prevent eccentricity and instability, we need to add a plate or another beam to the outside to support that overhang. Now in this case, we have shown beam B1A fixed to that existing beam B1. So to consider B1 and B1A as a unified section, we need to first work out the shear stress. Okay, now shear stress MPa, Newton divided by millimeter squared. We also need to understand the shear flow, which is Newton divided by millimeters. Okay, so we can work out the shear flow and we know the thickness. And then the shear stress is due to the beam flexure in the plane where the two elements are in contact, where the two elements are fixed. Now once we determine the shear stress, tau, we can then work out how many fixings, could be screws or bolts, required to keep both sections unified. We also note here that the fixings only have one shear plane, which means that the screws or bolts will only shear in one location. Now the other most important thing to note is that B1 and B1A must have the same modulus of elasticity in order to carry out that shear stress formula using a unified second moment of area, the moment of inertia I. Now, why do you think this may be the case? Have a think about it. Well, if we have two different materials, like the one shown here, then the normal flexural stress profile will no longer be a linear line. In fact, it will be staggered like this. And the flexural formula, sigma is equal to minus my over I, is no longer valid. Because if you think about it, Hooke's law states the stress is equal to E, the modulus of elasticity, multiplied by the strain of the material. Now the stress profile would be different for each material. So then we can no longer use the linear elastic analysis. Now if we had the same material like in this image here, then the stress profile would be linear and plane sections would remain plane before and after bending. So in this case, we could use a linear elastic analysis. Now, provided that we make sure that the shear stress between the materials due to the varying bending moments along the beam is less than the allowable shear stress of the fixings. Okay, whether you are using glue, nails, bolts, or screws, we need to check the capacity of these fixings to keep a unified element. But if you want to bond two different materials with two different modulus of elasticity, then we may need to adopt a composite beam analysis using the transformed area method. And that requires us to work out the modular ratio of the materials in order to work out a revised one equivalent material shape. And this is a very similar concept, if you like, to reinforced concrete. Yeah, so if the materials are the same, then we can simply work out I of the unified built-up section using the parallel axis theorem. Now, example 2. In this second example, we have two interesting built-up sections. In the first detail here, we initially had an upper wall, which is a double-featured wall, overhanging B1 either sides. So to provide a stable solution, we can actually fix two beams or two plates to either sides of B1. So here we have B1A either sides. Again, assuming we have the same modulus of elasticity, then we can work out the longitudinal shear stress on the faces where the elements are in contact. And then, of course, from there we can work out the shear flow and then the number of fixings required to keep these three elements in a unified section. In the second image, we have another interesting detail where there are two built-up sections to consider. So we originally had a wall height issue and an overhang issue as well in one problem. So we need to add another top plate, okay, to compensate for the height, and beam B1A over here to fix the overhang issue. So I guess in this case we need to consider the top plates, the shear stress through the top plates and the beam separately. For the double plates, the double top plates, the longitudinal shear stress is at this interface here, and then the shear stress for the beam elements would be through this interface here. Example 3. This is a very common example as well, where we have laminated beams. And as you can see here, in this model here, we have 3 laminated beams with either screws or bolts. And the shear stress in this case may be considered along each face where the elements are in contact. In this situation, where we have large loads and the beams happen to be LVLs, then I think you got to be very careful when laminating these beams with bolts. Why do you think this may be a problem, especially when we have LVLs? Well, due to the applied loads, we will experience tension perpendicular to the grains. The bolts will provide tension perpendicular to the grains, which LVLs are very weak at. In fact, almost every timber beam is weak when we have a force perpendicular to the grains. So we would need to check the bearing of the bolt on the timber perpendicular to the grain, as well as tension perpendicular to the grain. Now for this reason, sometimes using screws are a much better alternative. I guess I went off topic in this case, so we might discuss this in a different presentation. So yeah, this is a simply supported beam with a UDL, and I have also shown a point load in the middle. And here we have the shear force diagram, which is shown here. So at maximum shear force V, there would be maximum shear stress. And this is why we generally have more fixings at the ends and under the point loads, as you can see here. There is under the point loads, you will have a stepped up shear force, so we would need to provide more fixings in this area. Example 4. Yes, example 4. There are 3 built up sections here. I don't think they're very common. However, I believe they are fairly undermined a lot. The effectiveness of these built up sections can sometimes negate the use of large steel beams and columns if designed and constructed carefully. Forming a simple rectangular beam into an I-shaped section I believe can increase load carrying capacity by a good 30 to 50%. In the first diagram, we would need to consider the shear stress in the top and the bottom plane where the elements are in contact. But in this second diagram though, we need to consider the shear stress along both sides. And in the second diagram, it's probably more convenient to use it as a flexural member. And in that boxed up diagram, the boxed up section here, we check the shear stress on the sides where the elements are in contact to work out the capacity and the number of the fixings required to unify the section. Example 5. Yes, example 5 was an interesting one. We have a double cantilevered. We have a double cantilevered PFC and welded plates on top and bottom to support a large column from above, as shown here. In this case, we had a beam height restriction, so we couldn't utilize any bulkhead underneath, and one PFC couldn't carry the load. So by creating this built-up section, we were able to slightly increase the second moment of area of the unified section, as well as provide a better stable support system. Now, since the steel plates and the beams all have one modulus of elasticity, then we took these elements, the entire elements, as a unified section, provided though that we check the shear stress in the welds where there is a top and the bottom plates in these planes up here and down here. And the plates where the beams and the plates are in contact. So the plates here connects the two beams together, unifying it into one element. Example 6. Here we have three members, three built-up members, and they're common as well. The first one is when we need to create a complete custom member to suit, our design criteria. We could create our own UB or PFC sections, and again we need to calculate the shear stress in this area where the flanges and the webs are in contact. Because of symmetry, you can you can take it from one side only. You don't need to check both ends. And again, once we know what the shear stress is, we can determine the strength and length of welds required to unify the whole section. The second detail is an interesting situation where we need to stiffen the compression and tension flanges of the steel beam. And in most cases though, we should focus on stiffening the compression flange in the steel beams, to provide to prevent any lateral buckling. Steel is not the best in compression, so providing a stiffening plate will help in lateral buckling. Anyhow, the shear stress in this case would be examined in this area here, in this location. So we need to calculate the first moment of area. When we calculate the first moment of area, we should actually take the whole area of the PFC. And the distance y bar would be from the centroid of the PFC to the centroid of the entire section. The concept of the third detail is very similar to that second one here, as the idea of stiffening the compression and tension flanges with additional plates is the same, but the main difference is in the third detail we are welding the plates, while the second one we are bolting the plates. We can now go to example 7. Example 7 is also common. Say we have a 200mm thick suspended concrete slab on piers, and we want to add additional 100mm to the top for any reason, whether it may be a height issue or any other reason. Now this is to do this we need to calculate the shear stress between the existing and the additional concrete, then work out the shear flow per meter width of the slab. And once we get the shear flow, then we can determine the size and number of dowel bars required per meter run of the slab to unify the slab together, to unify these two sections into one piece. Example 8, and I think this is the final one for this presentation. Here we have a timber beam with a hole to allow for service pipes. And one of the solutions to this is provide a high-grade plywood board to either sides, as shown here. Now, plywood is a great material to take shear stress. Why do you think that is the reason? Because of their cross-laminate properties. That's why they use it a lot as a bracing board when we're bracing homes to take the racking forces. Plywood is a great way of going about it. And so this case here is another shear stress problem. We need to find the shear flow between the two elements, and then we can transfer the shear stress into the plywood via the fixings, which are generally screws. Now I personally would avoid using bolts for the same reason we spoke about before. Again, bearing and tension perpendicular to the grain is an issue, especially with large loads and large diameter bolts. So if you are using bolts, then just make sure to check for these design actions. So they are just some examples, but there are so many more that we can talk about. I hope by now I have convinced you and I have gained your interest in how important this shear stress formula is. In the next video we will go through the messy part, the derivation of this formula, and some worked out examples that could be helpful for you. In the meantime, we hope you've enjoyed this video, and if you have any questions, please write in your comments below. Please share and subscribe and like so that others may also learn. Until next time, we hope you have a great afternoon.